Hey everybody, I'm going to talk to you about Newton's third law. It's chapter 7 in Night. We've talked about the third law a little bit when we introduced forces, and now we're going to look at it in more detail and kind of how it affects our problem solving, and we do our force analysis. And in particular, it'll come in when we're looking at systems where we have two masses that are linked in some way, either just directly touching or attached by a rope or something else like that. So Newton's law, you've probably heard about, in elementary school and middle school in science, and they have learned that for every action, there's equal and opposite reaction. So that's common phrasing of Newton's third law. A different way to think about it is that a force is an interaction between two objects working equally strongly in opposite directions. We also talked about it when we introduced forces, that every interaction, right, there are two forces created, they work on different objects, but then they have equal magnitudes in opposite directions. So let's just look at a couple of visuals here, third law. So there is a hammer hitting a nail, right? So we know that the nail feels a force, right, because that's driven into the wall, but the hammer feels an equal opposite force that the nail exerts on it from that contact interaction. And if you've actually hammered a nail in, you know that if you hit it hard, right, the hammer can bounce back a little bit. So here's an example of gravitational interaction, right? The moon and the Earth are in a gravitational have gravitational force on that they exert on each other, and that's actually what's keeping the moon in orbit. So the Earth pulls on the moon, and the moon pulls on the Earth with an equal and opposite force. And then down in the bottom are just two boxes showing a contact interaction, and if they're pushed together, doesn't matter the direction or whether they're accelerating or not, the force that B exerts on A is equal and opposite to the force that A exerts on B. Okay, so let's look at a couple of examples of this. Okay, so in this, we have to try and sketch out what we think the free body diagrams look like for these cases, right? So we have, in all the cases, we have two boxes that are interacting with each other. It could be that they're the same mass, could be that they're equal mass, right? It depends on the scenario. And some of them are going at constant velocity and some are going at constant acceleration. So we need to we'll answer the question, right? So compare, for example, does block A exert a greater force on block B? Or does B exert a greater force, or do they exert equal forces on each other? And of course, the answer for Newton's third law is that their forces are always equal. Okay, but let's look at what that means for the free body diagrams. So I'm going to do two examples. I'll do the top two examples here. So we have the first one, we have B is a smaller mass, and that's kind of in the leading direction. A is a bigger mass. A is getting pushed, and they're moving together at a constant velocity. So let's look at that. So we have, just sketch it again over here. I'm going to get a little too close. Okay, so we have little box B, and then we have big box A, and I don't know, that was like 50 and 100, was that what it was, grams? Yes, 50 and 100 grams. Okay, let me make my box a little different. Get the shape right, okay. And then there's a push this way, right? And they're moving to the left at a constant velocity. Okay, so we need to draw what the free body diagrams look like of these. So what are all the forces that they're feeling? So for doing these, it's and at least my experience, it's easier to start with the box that's on the leading side, right? So they're moving this way. Let's look at B first. Okay, so we think about all the forces that are acting on B. It said in the instructions, I didn't read the full thing through, but there is friction between each box and the ground. Okay, so let's just start out. We know that there is a force of gravity on B. Okay, so I'm just going to put B over here. And then there's a normal force. There's no acceleration in the y direction, so those two are equal. Okay. And then I know there is going to be some friction that's resisting the motion of B. So I'm going to put that this way, force of friction. Okay. And so the only other interaction that this is having is the contact interaction between A and B. It tells me that it's moving at a constant velocity. So I know that the force that A is pushing on B has got to be equal and opposite to the force of friction. Looks like maybe I drew it a little bit too long. Let's put that back. Okay. All right, so that's B. Now what does A look like? So I'm going to draw my free body diagram there. Now A is twice the mass. The force of gravity is going to be twice as long. Okay. The normal force is going to be twice as long. Okay. Force of friction is mu times the normal, right? We haven't used that a ton yet. But so if my normal is twice as long and these are the same material boxes, my force of friction's got to be twice as long. So let's say like that's kind of how I drew it on B. I'm going to draw it twice as long on A. And that's my force of friction. Okay. Now, A exerts a force on B. B is going to exert an equal and opposite force on A. So I'm going to take this guy and flip it over here. And it's about half the length of friction. And this is the force of B on A. So A is trying to move B forward, B is pushing back, right? That's the third law. Okay, and now I can add in what the push is. So that's kind of my variable that I can use to make everything else work. So let's say that's the force of friction. I got to double that about to compensate. Sorry, this was the force of B on A, and then maybe this is the force of friction. So that has got to be the force of the push. Okay, so this and this are the third law pairs. Okay, so the next example I wanted to do was a little bit different. So we're going to have A and B with the same mass. So they're identical boxes, kind of, both 500, I think they're small in this case. And let's say it's going to accelerate to the left. So how would things be different? So let's again do our free body diagram. I'm going to do, I'm going to just keep my labeling the same because I had B in the front before. Okay, so we'll do B first. That's the leading block. And like I said, that's kind of easier to start out with. Okay, so we'll do our Y direction first, right? The vertical, we have force of gravity. And again, there's no acceleration. We're not in an elevator or anything, so the normal force is the same as gravity. Okay, there's going to be some force of friction as well. I could draw that. I made it a little bit shorter just so I don't end up with this crazy long forces like I had last time. Okay, and then now we know it's accelerating. So when I put in the force that A, right, so again, the forces are the same. They're just going to be different lengths. So A is pushing on B. So I'm going to go, it's got to be the length of friction plus a little more so that I get an acceleration. And that is the force of A on B. Okay, and again, we can just kind of note down there, right, that we know it's going to accelerate that way. Okay, so now if I look at my other block A, and everything is going to be similar because these are the same mass now, right? So I have force of gravity, I have force of normal, I have my friction, opposing motion. Now I got to add in my third law of force, right? So A is pushing on B, B is pushing back on A. So I'm going to take this length, right, just about the same length, and flip it over. So something like that, maybe. Check our length. It's a little short. Okay, so that is the force of B on A. Okay, so now I can add in the push as my last thing, right? So this is another push here. And it's got to be longer, so I can have my force about the length of force of B on A. That would balance that one. I got to add in again another length for friction, and then make it even longer so that I get an acceleration. And that's the force of the push. Okay. Those are fun. Okay, so there's more of those we'll do practice in class. Okay, so when you have two objects, it's pretty clear that when the boxes are touching, right? If there's some acceleration, they're going to have the same acceleration, right? So any objects that are constrained to move together will have the same acceleration. It is also true if they're attached by a rope, right? So if these two things are together and the rope is tight the whole time, if B is accelerating with a value A, whatever, this block is going to have the same exact acceleration. Okay, and then the other thing when you're looking at linked objects is that if they're attached by a rope, the tension throughout the rope is exactly the same, right? So it doesn't change. Okay, so let's look at a classic example called the Atwood machine. It's just an example that's done all the time as a nice illustration of what happens when we have two objects that are moving together. Okay, and we don't actually have any numbers in this one, so it's just big M1 on the left and little M2 on the right. So let's see, let's just kind of sketch that picture here. Okay, so we have a pulley, we have M1 on the left, and a smaller M2 on the right. Okay, and we want to find the acceleration. So we're not actually given anything specific, we just know M1 and M2. Okay, all right, so we know if M1 is bigger that my system is going to accelerate down this way, right? So M1 is going to drop, M2 is going to rise up. So here's the thing. When we do our free body diagrams, we're going to have to, we will look at M1 and M2 separately, and we're going to always define the direction of acceleration to be positive. Okay? So for our motion diagram, right, like M1 is going to be accelerating downward, right? Let's say for M1. And then we'd have the opposite, M2 going up. Okay, so if we look at our force ID, right, and do our free body diagrams for A, okay, so we have the force of gravity, so force of gravity on one, and then we have tension from the string. We've got to make that shorter so that it's clear that there's a net force going downward, and then our acceleration will be downward as well. Okay, and then the free body diagram on B, I'm going to have a smaller, oh sorry, 2, not B. I'm going to have a smaller force of gravity, and the tension is going to be the same, right? Because that's the same rope. It's the force that 2 is pulling on 1 and 1 is pulling on 2. Same force, just opposite directions there. Okay, and my acceleration, I'm just going to put it over here on the side, is up in that way. All right, so now we have to define our coordinate axis, which is technically was something we were supposed to do in step 1, but it's going to be different for these two. And so for each mass, we're going to say positive is in the direction of acceleration. Okay, so for this, sorry, I had A and B, these should be 1 and 2. Okay, so for 2, my x will be that way, not that we have any forces in the x direction, and my plus y is going to be that way. Now for this guy, I want acceleration, I want my positive direction to be down. Oh, my dog wants to come in, hold on. Okay, so that's my positive, and I can have x either way, but we don't have any forces in x. Okay. All right, so now we're going to go and sum our forces and see what we get. Sorry for that little delay there. Okay, so we're going to now apply the second law, right? So we have, and we'll do it for M1 and M2 separate. So the sum of the forces, right, as a vector is M1A And then for M2, we have the sum of the forces equals M2A. All right, and so we're just going to go to our free body diagram. We're just writing these as vectors first, not worrying about signs. We're just adding up all these forces, right? So we have tension plus the force of gravity equals M1A. And then we can go to column vector notation. Okay, so this is our X and our Y. So tension is just in the Y direction. I define my positive Y as down, so tension is negative. So I have 0x and I have negative T in the Y direction. Force of gravity has nothing in the X direction and it has everything in the Y, and it's pointing in the same direction as what I defined as positive. So this is plus M1G, right? That's the force of gravity, and 0 in the X. And then this is a scalar. Sorry, I didn't put the vector in there. So this just can get distributed in. So it's M1AX and M2AY. M1AY. Okay, there is no acceleration in the X direction. So now I can just bring down my Y equation. So I get negative T plus M1G equals M1AY. All right, now we do the same thing over here. So what are the forces acting on 2? So we have, again, we're just putting vectors down. We're not worried about plus or minus yet, what their direction is. So we're going to add tension and the force of gravity on 2, and that's going to produce some acceleration on 2. So we'll do our column vectors again for X and Y. It's just one-dimensional here, but it's good to just get in the practice of this. So for free body, for M2, right, we're saying up is positive. So now tension has nothing in the X direction, and it has a positive T in the Y direction. And then gravity has nothing in the X direction, and it's got negative M2G in the Y direction. And again, we'll distribute our mass in here, so M2AX and M2AY. And we know that's 0. So we bring down this equation, T minus M2G equals M2AY. Okay, now we have two equations. These two accelerations are the same, right? So we can just call them A. They're the same because they're going to be linked together. So two equations and two unknowns. The problem asks us to solve for acceleration. So we don't know acceleration and we don't know tension. Okay, but we can solve over here, let's say for tension, and then plug it in to the other one. That's fine. So T equals M2A plus M2G. Okay, and then we'll plug it in over in this equation. So we have negative M2A plus M2G plus M1G equals M1A. All right, now A is what we're trying to solve, so we'll group those together. So we bring that over here. So on the left, we're left with M2G plus M1G equals M1A plus M2A. All right, so we get M1 plus M2G equals, nope, I missed my negative sign here. So forgot to distribute that in. Why didn't you guys tell me? All right, so I have negative M2G, so it's M1 minus M2G, and then over here we have M1 plus M2A, and we can divide both sides by M1 plus M2. Okay, so we'll just finish over here. We get the acceleration equals M1 minus M2. I'm actually going to put G back in just so we can talk about this for a second. So it's M1G minus M2G over M1 plus M2. And that's our acceleration. And then we can plug in if we were given values, right? But look at what that's saying. So it's saying this is basically, you know, our acceleration is the net force over the mass. Okay, and if we think about these two things acting as a system, right, that our whole system is mass 1 and mass 2, then there's the weight of 1 trying to drive it to the, you know, counterclockwise, and then there's the weight of 2 opposing that. So if we look at the whole system, And just think kind of the external forces. M1G is trying to accelerate it, so that M1 drops, and then M2G is opposing it. So this is really the net force on the system, and then our system mass would be the sum of them, M1 and plus M2. So it's kind of cool in that tension actually doesn't affect anything, right? I mean, we could think about this as just the system of the two masses and not even worry about tension, and just look at what are the forces acting external to them, which is the force of gravity on one, opposed by the force of gravity on two, and it's got to try and accelerate the combined mass of two of them.